Hey everybody, for this video I want to basically take a deep dive and look very deeply at calculus in a particular way, not like any real analysis type thing, but I do want to investigate kind of the functions behind what a derivative and what an integral is. I could also look at what limits really are, but that's a whole different thing. I could do that in a separate video. So let me just basically think about it. So a derivative, let's first think of the mapping. So the domain of a derivative, so I'm going to call the derivative d. Okay, let me make that a little nicer. So it's so d, and it maps from, well, obviously the set of differentiable functions on a particular interval. So I'm just for the sake of this video, I'm only dealing with derivatives in the real line, basically, and derivatives in R, basically. So it'll take the set of differentiable functions, which I'm going to denote with a like a calligraphy D. No, that doesn't look good. It's been a while since I've written these. Something like that. So it's going to take the set of differentiable functions on A to B, and it's going to output them to the set of functions from R to R. Now they're not necessarily continuous because you can have you can pretty easily think of some examples of derivatives that are not continuous. Like, for example, if you're taking the derivatives of a bunch of like piecewise functions, then you're going to have like one of the slopes is going to be here, and then the other is going to jump up to here or something. So you can think of some examples that are not continuous. So they're just general functions, which I'm going to denote with a calligraphy F. So something like something like this, something like that. From R to R. These are just common notations that I see, so I'm just mimicking that. And so yeah, this is the derivative, not necessarily evaluated at a point. It's just the general derivative. So once you take like d over dx of a function f of x or something like that. Now we could look at something like the derivative evaluated at a point, I'll say x0 or x0. So again, the domain is going to be the differentiable functions on an interval a to b, an interval of the real line. And the output is going to just be r, because obviously you're going to have the derivative there. And actually, now that I'm thinking about it, sometimes the derivative is undefined, so I don't think that impacts anything, but whatever. But yeah, sometimes it's undefined, so I'm not sure where that fits in, but I don't know. And so we can now think of something like, we can look at like kind of the abstract algebra portion of this. Consider the kernel. So the kernel of a function, so let me just write over here what a kernel is. So the kernel of a function, I'm just going to call the function f, is basically the set of points x such that f of x is equal to 0, or really whatever your identity of that set is. So all the points x such that f of x equals 0. So not that bad of a definition. Let me adjust this curly brace here. And so basically, we can consider the kernel. So the kernel of d, of our function d. So what this is going to be, it's all basically every function such that whenever you take its derivative, so if we have df over dx, we're trying to find when df over dx is equal to 0. And so we can multiply both sides by 0, so we get df equals 0 dx. And now technically that's just 0, but we can integrate both sides and see that f, or f of x, has to be equal to, well, the integral of 0 is just going to be 0 plus c, so it's going to be some constant c, where c is just in the real numbers. So basically what that means is the derivative of a constant is equal to 0. And that's the only thing that's equal to 0. So I'm sure you knew already that the derivative of a constant was 0, but I was just looking to see if there's any other possibilities, and from this it doesn't look like there are any. So the kernel of d is just equal to the set of real numbers, and that's just r. Let me make that nicer. And so yeah, that's basically, that's not a really difficult thing. Now, if we're trying to evaluate the kernel of d of dx naught, that's going to be more difficult because you're trying to find because that really depends on what x naught is as well. So that's a little more challenging, so I'm not really going to consider that case. Let's meanwhile look, let's take a jump to the integrals. So integrals, we're considering Riemann integrals here. This is going to be a mapping from the set of integrable functions, so Riemann integrable functions. I don't really know how to do a calligraphy I, but I can do something like that, something like that. I don't know. Integral functions on A to B, that is a hard word to say. And then our output is again just going to be functions. So functions from R to R. Okay. They might not be continuous, so I'm not going to say it's the continuous functions because they could totally not be. And then if we're considering the integral from A to B, which I'm just going to denote it like that, this is again the set of integrable functions as our domain, and our codomain is just going to be R. So pretty much the same setup that we have here. And then the kernel of I, again, I'm not going to consider the kernel of I from A to B because that also depends on what A and B are. So the kernel of I, well, this is hard because if we're taking the integral of a function, like it's really, like if we want to try to find it, so we can see integral of f of x dx, when is that equal to 0? Well, we can take the derivative of both sides and we get f of x is equal to 0. Okay, let's just plug that back in because that seems to be our only answer, but let's just make sure. So the integral of 0 dx, well, remember, we just said that was c, where c is just a real number. And so we don't actually get 0, we get a constant. So that's the issue with integrals, is that we have this up to a constant thing. So what you could maybe say is that the kernel of I is simply just equal to, it's simply just equal to, oh my god, I cannot write a curly brace. It's simply equal to the set 0, up to a constant, yeah, so up to a constant, if you just want to consider that. And again, it depends on what that constant is, but if we're considering it up to a constant, then that constant's irrelevant, and we're just left with the set 0. So that's kind of that case. It's kind of a weird case right there. And one thing I do want to mention is that I talked to some people about this, and the derivative thing is totally fine. The thing with integrals is that apparently there's some weird thing with the axiom of choice from set theory, which I don't ask me, I don't know much about that. So apparently this is not a totally functional system, and it's not the best way to define it, and I don't think there even is really a good way to think about this mapping, but this is kind of just what it kind of looks like, so I think it's good enough. This is kind of a more informal video anyway, so don't worry about it. Let's see, so the limit is another thing I want to think about, but that's really hard because, actually I'll just talk about it. So the limit, I'll call it a function L, that actually has two inputs. We have, what we have is the actual function, so it comes from some sort of function space, which I'm just going to call it I'll say F prime, because I don't want to confuse it with these. It's some sort of function space, and actually I'll just call this F1 and F2. Some sort of function space, it could be from real to real, or subsets of the reals, or something, I don't know. But it's that, and then we take the Cartesian product with just a constant, so the limit, the limit as x approaches some number. So that, really what that is, it's the extended real numbers. So it's R union plus or minus infinity. Oops. Or you could just say R bar. So that's just R with a bar on top, but I just want to, be totally formal there. So that's the domain. It's a two things there that you're considering. And then the output is again R bar, so R union plus or minus infinity. Now the issue is like, the function space is something that we don't really know. We don't know which ones will totally work because it also depends on this, and it's just a complicated thing. So this sort of like functional analysis that we're doing, it's interesting, it's motivating, but it's not totally formal, and there are certain holes in here that I don't know. Just I would suggest looking at Stack Exchange. I found some things about this limit thing on Math Stack Exchange. So if you want to learn more about that, I think if I find it again, I'll leave a link in the description below. But yeah, I hope you enjoyed just a little bit of a deep look at calculus and a little bit of functional analysis. So I hope you enjoyed. Thank you so much for watching, and I will see you in the next video. Bye, guys.